Section 6C, the normal distribution. In Section 6A, we introduced the shapes of several different types of distributions, and one of those was the bell-shaped distribution. In a statistics class, it's more common to refer to the bell-shaped distribution as a normal distribution. So let's look at the official definition. The normal distribution is a symmetric, bell-shaped distribution with a single peak, and its peak corresponds to the mean, median, and the mode of that distribution. One of the things that affects the shape of a normal distribution is the standard deviation, so let's look at that definition. The standard deviation of a normal distribution is a measure of how much variation there is in the distribution. The symbol for the standard deviation is sigma, and the larger the standard deviation, the more variation there is. And the smaller the standard deviation, the less variation there is. And when we meet together in class, I'll show you an application that shows you how the standard deviation specifically affects the shape of the normal curve. So the empirical rule is also known as the 68, 95, 99.7 rule for the normal distribution, and that's the way they're referring to it here. But that is commonly known as the empirical rule, so I'll write that name on the side as well. So we use those interchangeably, the empirical rule and the 68, 95, 99.7 rule. And what this rule says is that for a normal distribution, about 68%, or just a little over 2/3 of the data, fall within one standard deviation of the mean. About 95% of the data fall within two standard deviations of the mean. And about 99.7% of the data fall within three standard deviations of the mean. And they have a picture of that here for a normal curve. If you have your mean in the center and you add one standard deviation to that to the right and to the left, then that's creating this set of boundaries right here. And they're saying if you look at how much data is in that section, it'll always be about 68% of your data for a normal distribution. And then if you go out a little further, twice as far in fact, and you go two standard deviations to the right and two standard deviations to the left, and you say, okay, how much of my data fits in this range? You should find that that typically ends up being about 95% of the data for a normal distribution. And then if you went out a little bit further still, three standard deviations to the right and three standard deviations to the left, then you would get almost all of your data. This 99.7% is what you would expect. And there's only 100% of the data overall, right? So by the time you go out three standard deviations in each direction, you're going to pick up almost everything. So there's a little bit that's left on the outsides. I guess if you look at 100 minus this, there's 0.3% left for the outsides, but not very much at all. And if you want to use this rule and think about applying it to different applications, then you have to be aware of how far away you are from the mean measured in standard deviation. So you need to know somehow if you're given a value, is that one standard deviation away, two away, and is it to the right, is it to the left? And we have a tool for determining that, and it's called a standard score. Another name for a standard score is also a z-score. I'm more likely to refer to things as z-scores than standard scores, but again, these are interchangeable terms. And the z-score is the number of standard deviations a data value lies above or below the mean. That's called its standard score or z-score. And the way you get that z is you take the data value, you subtract the mean, and you divide by the standard deviation. And when we turn the page, we'll see some examples of how this works. The standard score ends up being positive for data values that are above the mean and negative for data values below the mean. So when you compute a z-score, you know how many standard deviations away from the mean you are, and you also know in which direction. And again, that's going to be somewhat important for us, because if you want to talk about the 68, 95, 99.7 rule, it's making a reference to how many standard deviations away from the mean you are. Is it one standard deviation? Is it two standard deviations? Is it three standard deviations? So the z-score is going to give us a tool to help us compute how many standard deviations away we are to either side. And the z-score, by the way, and the normal curve are both vital in statistics. So the topics we're talking about here, the better you know them, the more of a head start you'll have when you make it to your stat class. Okay, let's go ahead and look at an example of how the empirical rule can help us answer questions about a normal distribution. The resting heart rates for a sample of individuals are normally distributed with a mean of 70 and a standard deviation of 15. use the 68, 95, 99.7 rule to find the percentage of heart rates in each of the following categories. And the first category they want us to do is less than 55. So here's my strategy on this. The first one is I want to visualize it. So I'm going to draw in a bell-shaped curve. So I'll draw in my axis, draw in a bell-shaped curve, and near the peak, if I drop down, that's supposed to be the mean. And it says in the problem that we have a mean of 70 for this distribution. So I'm going to put 70 right there. And then the next thing I would do to start thinking about the 68, 95, 99.7 rule, or the empirical rule, is I would want to count using the standard deviation of 15 in each direction till I got 3 standard deviations on each side, and that would be about the flattening out spot. So I want to kind of think about making 3 tick marks to get to the flat spot. 1, 2, 3. And that should be about 3 standard deviations. So I want to add 15 to this, which would be 85. And then add 15 again, which would be 100. And then add 15 again, which would be 115. And that would represent 1 standard deviation to the right, 2 standard deviations to the right, and 3 standard deviations to the right of the mean. If you want to move in the other direction, then you'd want to subtract 15. But we still want that same idea, that it's going to be 1, 2, 3 tick marks, and then we're at the flattening out spot. So this time I'm subtracting 15. So 70 minus 15 would be 55. And then subtract 15 from that, we would be at 40. That would be 2 standard deviations to the left. Subtract 15 again, and we'd be at 25, and that would be 3 standard deviations to the left. And now that I've got that labeled, I want to think about their question. And what are they asking us? What percentage of the heart rates are less than 55? So I'm going to draw a line at 55, and then I'm going to shade the part of this curve that is less than 55. And I can try and use the empirical rule to think about what that would be. So here's how I'm going to do that. First of all, I want to think about this 55, how many standard deviations away from the mean it is it? And because the way we counted this, we should be able to just tell that was 1 standard deviation to the left. We could also use our z-score formula, which might be overkill here, but you could do the 55 minus the mean, which was 70, and divide that by the standard deviation, which is 15. And in this case, the numerator would be negative 15, denominator is 15, so you'd get negative 1. And again, we mentioned on the previous page that a negative on a z-score means you're to the left of the mean, and the number is how many standard deviations. So I would read this as telling me that 55 is 1 standard deviation to the left of the mean. But I could already see that on my picture because I had numbered things by counting standard deviations to the left and standard deviations to the right. So what you want to do to use the empirical rule is if your boundary is 1 standard deviation away, then you probably want to go ahead and draw in the other mirror image boundary that's also 1 standard deviation away. And you can see I kind of have a lack of symmetry here, so it's very rare you're going to hand draw one of these curves perfect. But this area right here, in between 1 standard deviation to the left and 1 standard deviation to the right, if we look at the empirical rule, if you go 1 standard deviation right and 1 left, you're supposed to have 68% of your data right there. So I think that in the middle, I should have 68%. Now I don't want the middle, I want this left side, but by figuring out the middle, it gets me started. If we think about the middle, we could then say, well, how much is left over? And we could say I can take 100%, which is the total amount of data, and subtract the 68 that's in the middle, and that would leave 32. But where's the 32? And the answer is it's not in the middle. But it's not necessarily all over here, and in fact, because of the symmetry of the curve, this 32 should be split up among the 2 outside pieces. So my next calculation would be to take that 32, cut that in half, and that would be 16, and that should be the percent on each side. So I think that right here, I would have 16%. And on the other side, right here, I would also have 16%. But the only part I want is this part I've shaded in blue, and that would be 16% according to the empirical rule. So that's a little bit interesting. I'm using the 6899.7 rule to find the answer to this question, yet the 68% that comes from the rule is not my answer. but I used that 68 to think about what was left over and then to split that in half and to ultimately answer my question. I also think this would be very difficult to do if I hadn't drawn a picture. So I would definitely recommend on all of these that you start off with a picture and that you do this numbering on both sides using the standard deviation as your scale to mark off 3 notches to the right and to the left. Alright, let's go ahead and move on to part B and try another one of these. This time they want to know the percentage of the heart rates that are less than 85. So I'm going to start off in the same fashion that I did last time by drawing the picture. This time it'll go a little bit faster, but I'm going to number it in the same way. If I drop down from the peak, that should be the mean, and the mean of the curve is 70. And I'm going to go 1, 2, 3 notches to the right. It's the same numbering as last time, so this would be 85, 100, and 115. And on the other side, same thing, 1, 2, 3, and you should be roughly where the curve is disappearing. And that should be the 55, the 40, and the 25. And then I would want to think about the number they're asking about, which in this case is 85. So I'd draw a line at 85, and then I would shade what they want me to find, which would be everything to the left of 85. And then I would argue that the work I did above is mainly going to answer this question for me. If I drew another line at 55 right here, then I already know from the work up above that this area in the middle should be 68%. That's from the empirical rule, and that's the amount of data that's within 1 standard deviation of the mean going both to the left and the right. So that's this section right here. And then we also know from the picture up above the amount to the left of 55 is 16%, and the amount to the right of 85 is 16%. So in this case, I want the amount of area that's to the left of 85, and I've got that in 2 chunks here. There's 68% of it in the middle, and then another 16% off to the left. So I would say the answer to this question is the 68% in the middle plus the 16% that's over here on the left-hand side. That gives me the total amount that's to the left of 85, and adding that together, I have for Gary the 1 looks like 84%. So that should be the amount of area that's to the left of 85, or the percentage of heart rates that are to the left of 85. Just a quick mention, there's another way I could have done this and still got the same answer, and either one of these would be fine. Another approach to this would be to say the graph represents 100% of the heart rates, and if I look to the right of 85, I have 16%, and I want less than 85, so I don't want these. So I could say when I go to answer this, I want all the heart rates except for the 16% that are above 85, and that should just leave me with the ones that are less than 85. And if you do that subtraction, you get 84%. And again, same answer, so either approach would be fine. I think this is more direct because we're thinking exactly what they want, what's less than 85. But when you get to statistics, you'll find it's very useful if you have this flexibility to sometimes, instead of finding what you want and adding those together, to maybe sometimes subtract out what you don't want from 100% and get your answer that way. Alright, let's move on to another one. In part C, they want to know what percentage of the heart rates are greater than 100. So like I did on the other ones, I'm going to start off with a fresh picture and draw my bell-shaped curve. Dropping down from the peak, that should be the mean, so that would be 70. I'm going to go 1, 2, 3 notches to make it to the flattening out spot. Those numbers would be 85, 100, and 115. Again, just a reminder, our standard deviation was 15, so I'm just adding that 15 over and over again. And then 1, 2, 3 notches to the left would be 55, 40, and 25, and that just goes from subtracting 15 once, twice, 3 times. And then I'm going to mark the number that they're talking about, which is 100. So that's right here. And then how many standard deviations to the right is that? We could do a z-score, but we can also just count 1, 2. If I'm going to go 2 standard deviations to the right, and I want to use the empirical rule, then I'm also going to go 1, 2 to the left. Because the empirical rule's 3 numbers, 68, 95, and 99.7, apply to going 1 standard deviation in each direction, 2 standard deviations in each direction, or 3 standard deviations in each direction. So once I see on the picture that I've gone 2 standard deviations to the right, I want to go 2 to the left as well. And then what I would know from the empirical rule, switch colors, is that in between these two, since that's 2 standard deviations out, I go ahead and bring the empirical rule back in for a second. If we go out 2 standard deviations in each direction, we should get 95% of the area. So the area in the middle right here should be 95%. And now just thinking about what that means in terms of their outside tails, I'm just going to do a little bit of math there. I know it's 100% overall for the picture. If I subtract 95, that's 5% left over. But where is that, on the left, the right? The answer is split among the two. So if I take that 5 and I cut it in half, that would be 2.5% on each side. So this is 2.5% and this is 2.5%. So I think I've got a decent picture at this point, but now what is it that I want from that picture? I want the areas that are, or the heart rates that are greater than 100, and that would be these to the right of 100 right here. And based on the 95% in the middle, we split it out and said 2.5% on each side. Well, that 2.5% right there are the ones that are greater than 100, and so that would be the answer to that question based on the empirical rule. Alright, let's look at one final one. This one actually turns out to be the easiest one, I think. Trying to do the area between 55 and 85 to estimate the percentage of heart rates in this category. So I'm going to start off drawing my bell-shaped curve. I'm going to drop down from the mean and from the peak and put the mean, which would be 70. I'm going to count 1, 2, 3 notches to flat. That'd be 85, 100, and 115. And 3 notches to flat on the left. 1, 2, 3 would be the 55, the 40, and the 25. And then I'm going to mark off the ones they want between 55 and 85. So 55 is here, 85 is there. And fortunately this time that's the same distance in each direction. So I said this was probably going to be the easiest one because all we really have to think about is how far did we go in each direction. And we went 1 standard deviation to the right and 1 standard deviation to the left. So according to the 68, 95, 99.7 rule, since I've only gone out 1 standard deviation on each side, that should be about 68% of the data, or in this case 68% of the heart rates that fall into that category. Alright, so there's our first example on the empirical rule. This can be a little bit of a tough topic for you to digest, so you might even have to come back, watch this again to kind of see the thought process. And we also have another one on the next page.